Hey guys, how's it going? So today will be the first video in my summer research vlog. Um, Partially for whoever's curious on YouTube, mostly so I can send it to my mom and my dad and my brother because they're curious what I'm doing. But I hope you guys are curious as well. So before we jump into some of the heavier physics stuff, I'm just gonna give you guys a quick little tour of the lab that I'll be working in this summer. It's nothing fancy, but it is really cool. This is Dr. Daniels, my professor at UNCW. This is his own nuclear physics lab. Call it Daniels Lab. And so I'm just giving kind of a broad tour. This right here to the left, I'm about to go back to it, is the actual chamber that we're going to be using for the summer project, which I'll get to in just a minute. But that's the main event there. So what we're actually going to be doing is what's called Rutherford scattering. And so here is the classic layout of a Rutherford scattering experiment. It's a nuclear physics experiment. And in the early 1900s, Ernest Rutherford, along with some of his graduate assistants, discovered that the atom is not like the plum cake model that they theorized, where charge was distributed equally, positive and negative, but there's actually a centralized positive nucleus, and the negatively charged electrons orbit around that. And the reason he was able to figure that out was through this thing called Rutherford scattering. So basically, the idea is that you generate a beam of alpha particles from a radioactive source. Alpha particles are positively charged decay products from alpha decay, and you let them be incident on some kind of foil. In the classic experiment, it was gold foil. For ours, we're going to be using tantalum, which we'll get to in a second. And essentially, the alpha particles, some of them will just go through the gold foil undeflected, but some of them will go really, really close to some of the atoms inside of the foil, specifically close to the nuclei of some atoms in the foil, and they will scatter. And you can detect these scatterings, and it can be used, for our case, we're going to use it for calibration purposes. Dr. Daniels works with Tunnel at Duke University, and he's going to build this detector with us that I showed in the video, and we're going to set up this Rutherford scattering experiment, hopefully, and use it to calibrate his detector so he can take it to Tunnel and hopefully put it to some good use in some proton-proton scattering experiments there at Tunnel. So a couple of the things we'll be doing this summer that I'll talk to you guys about is what goes into formulating the experiment itself. Um, the first day was today, so you guys are getting it right from the start. I'm going to be learning a lot this summer as well, so hopefully I can share some of that with you guys. And so yeah, we're just going to go through kind of how nuclear physics experiment works and give you guys a little bit of insight to what undergraduate research project looks like. So to start out, I'll just show you guys what I was doing this morning after Dr. Daniels was so kind to make me some coffee. So the first thing that Dr. Daniels wanted me to do was generate a plot of the cross section for an alpha particle to scatter dependent upon the angle that it scatters at. So cross section in nuclear physics essentially just means the probability for an interaction to occur. And so in this case, the cross section is telling you the probability that the alpha particle will scatter at a different angle. And as you can see, the cross section steeply decreases with an increase in angle. And that's because the actual Rutherford scattering equation for cross section goes something like 1 second. So there's some constant here which I won't verify for now, but that big constant is multiplied by 1 over sine to the 4th theta over 2. So there's an inverse relationship between angle and cross section. So as you increase your angle, you're going to get a smaller and smaller cross section and a lower probability to scatter. So, and this is shown in Rutherford's classical scattering setup. It's much less probable to scatter at large angles. However, it is possible, and that was what determined the nucleus being inside of an atom, the nucleus model of the atom. So he wanted me to generate this plot, partly just as an exercise to make sure that I could run some code. My coding experience isn't grand. I've had 1 semester of computational physics, which I just finished about a week and a half ago. So that's the extent of my coding. However, I know enough, and it's specific for physics. So, I was able to figure it out with a little bit of debugging. So that's our cross section versus scatter angle. And the next thing that Dr. Daniels had me do was he wanted me to look at change in incident angle. So from the way that he described it to me, and now some of this is still a little bit over my head, I got to talk to him tomorrow a little bit more. But essentially, we have our source over here that's going to be decaying, and it decays isotropically, which means evenly in all directions. And what we want to do is we have this foil over here that it's going to be incident on, and we want to actually constrain a beam of alpha particles to come in on our foil. And based on how narrow that channel is, it can generate different angles for alpha particles that are at the edge, which in that case will change the angle in which they scatter when they hit the foil. So again, I'm not super up to par on that explanation. Hopefully in the few coming weeks I'll be able to give a more intellectual explanation on that. But the main product really is the code and the graphs that I was able to generate for Dr. Daniels, and he'll probably explain to me more tomorrow what all that means. So I'll get back to you guys on episode 2. But basically what he asked me to do is he wanted to know how sensitive the cross section was to differences in angle, incident angle changes. And so what he had me do was calculate the cross section at 15 degrees and then calculate subsequent differences of 0.2, 0.4, 0.6, and 0.8 changes in angle plus or minus, which is what you see here. So for this one I did 15 plus 0.2 and 15 minus 0.2 and grouped those two together and took the difference between them, their difference in cross section, and then divided it by the cross section at 15 degrees to get the fractional difference in cross section. And so these are the results of that, right? So this is the fractional difference in cross section for the different groups that we have up here, ranging from changes at 0.2 and up to 0.8. And this was at 15 degrees. And so this was the plot that was generated. It's a linear dependence, as you can see. And he wanted me to do the same kind of thing for larger scattering angles, particularly 45 degrees and 90 degrees. And so same kind of code running for those two as well. That's why I didn't want to put it in there twice. So similar kind of code for 45 and 90, and these are all 3 plots put together in one graph. And as you can see, they're all linearly dependent on the cross sections, dependent on the change in theta. However, the steepness decreases as you get to larger scattering angles. And that makes sense because if you look at our original graph here, you can see that, around 15 degrees, it's a pretty steep graph there. And as you jump up to 45, it's not as steep. And then up at 90, it's even less of a steepness there. So, and that's basically what those changes are telling us, right? We're starting at 15 degrees. We're going a little bit less, a little bit more, a little bit less, a little bit more, and just getting a average for that. So that was that, and again, I'll have some more insight on that tomorrow once I talk to him. But the last thing I did, and then I'll tell you about one more thing, was I needed to get the current activity of our source. So we're using americium as our radioactive source of alpha particles, and it's really important to know the source activity, because if you don't know the source activity, then you can't figure out how many alpha particles you're actually going to have in your beam per second. So I had to go ahead and calculate that, and it's a pretty easy calculation. It's just the activity today equals the initial activity times an exponential, which is the time elapsed, and tau is 1 over lambda, where lambda is the decay constant, which you can see tau is found by taking the half-life of your source and dividing it by the natural log of 2. Don't ask me where the natural log of 2 comes from. Not too sure on that. However, I can get back to you guys on that. But this is the equation, and it's basically just, plug and chug. I went ahead and just did it in Python. Just easier that way, so I have it all with the other stuff. The last thing I had to do is, if you notice the units here, millibarns per steradian. So millibarns is a cross section unit that is standard in nuclear physics, but it's not necessarily standard in other parts of physics. So it's important to highlight that I did have to do some unit calculations for my differential cross section equation. So I mentioned in the beginning that big constant I had to find, which shows up in all of my graphs, this cross section constant here. And what you basically have to do is, your Rutherford scattering equation is 1 over 4 pi epsilon 0. Epsilon 0 is a constant that you find in E&M. It has to do with the permittivity of space in a vacuum. And so that's the reason for the chamber. Probably should point that out. It is a vacuum chamber. Not functional right now, but that's another part of the project that will be fun, is getting to make it operational. So, and this is multiplied by the atomic number times the Coulomb, the fundamental charge constant squared, divided by the kinetic energy of the incident alpha particle, and this whole thing is squared. So when you do all of these units, I'm not going to run through it again. You pop out meters, and then you square that. You end up in meters squared, and 1 millibarn is equal to 10 to the minus 31 meters squared. So the value I got for this constant, given our atomic number of tantalum, this is just a constant, and the incident kinetic energy of our alpha particle, I was able to calculate this constant in meters squared, and then I just ran this conversion here and converted it into millibarns. And it ended up still being really, really, really small. It's 10 to the minus 9 millibarns, which is almost close to femtobarns. So, but not quite. Anywho, I think that's going to do it for today. Don't want this to run super long, but I'll see you guys tomorrow.